Hello everybody. So in this talk I will give an addendum concerning the future work we have to do for a complete implementation of our neural model of speech production and speech perception, which we have developed in the NENGO framework. And in the 5 earlier videos I gave a full description of the model as far as we have developed it and as far as we can do simulations using this model. But the work which still has to be done is an integration of the articulatory-acoustic model. So the results, the simulation results shown so far concern the cortical part of the model. So going in the model again, so what we have seen is the output here and down to this level, and at least we have implemented this part of the model. What's missing is still the implementation of a mental syllabary and the integration of the articulatory-acoustic model and the generation of the feedback signals of the acoustic and somatosensory feedback signals. Okay, so the work we have to do is to develop a temporal control model for syllables and for speech gesture coordination. That means we have we already defined neural activations for motor plans, but they have to be specified concerning the execution of motor plans. So we have to specify motor plans concerning the control of the timing of the start and ending point of actions or speech gestures. So what are actions or speech gestures? So if we plan to produce a syllable like pa, we have to implement a vocalic gesture, the R gesture, which also is called vocal tract action or vocal tract form action in this case. And we have to specify consonantal gestures like for a B in the case of the syllable ba, consonantal gestures or actions which can be labeled full or near clothing actions at different constriction locations, for implementing plosives, nasals, or fricatives. Fricatives are the near clothing gestures. Plosives and nasals are the full clothing gestures. We have to implement glottal gestures or glottal actions, phonation actions or glottal opening actions in order to be able to produce voiceless versus voiced sounds. And of course we need to be able to implement full closing actions for the glottal stop. And we need to define actions controlling the movements of the velum. So actions concerning opening and closing of the velopharyngeal port. The opening gesture would lead to nasalized sounds or nasals. Closing is at least necessary for all other for the production of all other sounds, and especially full closing velopharyngeal port actions are necessary in the case of the obstruents, plosives and nasals, plosives and fricatives. Okay, so how to implement this part of the model? How to implement the articulatory-acoustic model integration. So what we want is to build up a neurobiological control concepts for speech movements, including the generation of for producing articulatory movements and at least acoustic speech signals. So what we want to do is the modeling of articulatory gesture and the modeling of the timing. When have we to start with the consonantal, with the vocalic gestures, and when has this gesture to end? That means we have to develop a phasing concept for the timing of gestures. And you may know from this vocabulary that this equals a concept which has been developed as articulatory phonology or as quantitative articulatory phonology by Brauman and Goldstein in the 19th of the last century at the Haskins labs, and this research is now going on in many places like the University of Southern California. In in concurrence to this model, our model concept is, yeah, as I told here, implemented as a part of a neurobiological based brain model. And so our emphasis is on a strict neurobiology implementation or inspiration for that model. So we will see we use neuron ensembles as a basis for implementing oscillators. And oscillator theory is also a part of articulatory phonology, but we use a real, that should be leaky integrated fire, LEF neuron models as basis. So we have spiking neurons which control the oscillators, and that differs from articulatory phonology, at least on the level of the implementation. So, oscillators is the first very important control concept if we want to generate the timing control for gestures, and if we want to generate the gestures themselves. So we need, or we can use buffers for controlling articulators, or more simple, we can use neuron ensembles. For that, no, it should be buffers. Sorry, it should be buffers in the concept of NENGO. So if we use buffers with recursive neural connections, we know directly from the earlier talks that allows us to define short-term memories. But in addition, recursive neural connection, that means neural connections which coming out of a buffer and going back to the same buffer, these kind of recursive neural connections allow as well the simulation of neural oscillators. How does it work? Imagine you divide the neural buffer in two different parts of neuron ensembles, or let's say at least just two neuron ensembles, and we transfer the energy by these recursive connections from one neuron ensemble to the other, and then back from that neuron ensemble to this neuron ensemble, back to this, and so on. Then we can generate a kind of oscillation of the energy of the neural activity occurring over time in this buffer. And that is, some results are given here for a neuron ensemble which just uses for a neuron buffer just built up of two neuron ensembles. In this case, we have two dimensions and can decode the output of these two dimensions. Let's first of all see what's going on here. So here we have the energy of or the articulatory activation, the neural activation of one buffer, and we see in blue, and of the other buffer in green, and what we see over time is that we get an oscillatory behavior. The energy changes from one part to the other. And here we see time just as a parameter, and we have output 1 against output 2, and what we see is here that we again get an oscillation. I think here in the clockwise direction, we will see in our modulations it will be counterclockwise. Okay, so what we now want to discuss is how can we come from the phonological form activation to motor plan activation, and how can we come from motor plan activation to gesture activation, including the temporal coordination of that. So as we see here, I did not emphasize it directly, but it is indirectly clear. The syllable is the basic unit, and the motor plan controls each syllable. And what we will see in our model is that motor plans are stored as a whole for all frequent syllables occurring in a language, and that is called the mental syllabary. So motor plans store the timing or the phasing of smaller units, that means all the vocal tract actions. At least these vocal tract actions are the basic motor control units directly controlling the speech articulators. And the phasing for, or the timing for these actions is stored in the motor plans, and motor plans are stored for each frequent syllable of a language. Yeah, first of all, let's have a look. So here, have a look in the organization and the architecture of the model. So here we have our motor plan level, set of motor plans for all frequent syllables of a language, and we will see they do not just code the phonological form, but as well the somatosensory and acoustic form. And from that, we can generate a time series of gestures. Okay. So here we see, oh, I'm sorry, I forgot to say what is important, why is the acoustic and the somatory representation of a syllable important as well. So that is important because otherwise we are not able to learn the phasing of gestures or the motor plan of gestures, because we cannot learn them directly. We have not implemented them in the brain. We can learn them from the auditory forms. So going to this model, we need this somatosensory and acoustic feedback loop, including the not the inner loops, but the internal loops, but the external loop. So the real loop which generates an acoustic and somatosensory signal, and this output generated by our articulatory organs is important for at least learning the phasing of this gesture. So here we have a learning cycle. So we have an idea how our syllable timing should be, and we produce a syllable, then we get the acoustic and somatosensory result, and we can compare the acoustic result to acoustic impressions we got from our caretakers, from our parents from which we learn the language, and then we can refine the timing, the motor plan, produce it again to a degree of perfection for each syllable, so that we are satisfied by the acoustic result we produced. Okay, so here we get an idea how the mental syllabary and the gesture repository is implemented. We store about 2,000 syllables, all the frequent syllables for a language. That may differ, of course, from language to language. These syllable plans are stored as oscillators, as neural buffers, so recursive neural buffers, which represent oscillators. And at least there should be 2,000 oscillators here. At the next level, we have the gesture level. The mental gesture repository. Here it was the motor plan repository. And here we have just about 40 oscillators which represent different gestures. Here a few vocalic gestures. So in the case of modeling just 3 syllables, we just need 3 vocalic gestures. Normally here we have more oscillators representing all vowels occurring in a language. Here we have the gestures for controlling the velum and the glottis, and here we have the consonantal closing and near closing gestures. So that are the motor units directly controlling the articulation. That are the motor units controlling the timing of gestures. And this leads to an activation going to the primary motor cortex. That means the activation degree for each gesture is given here in order to control the muscles of the articulators. Okay, what we see here is a similar representation, but now it was directly generated by NENGO. So NENGO has a graphical user interface. The simulation results we have shown before were generated by using NENGO in a Python interpreter. That is different. So, and then we can use the matplotlib for calculating the activation plots for each buffer over time, which we saw in the earlier talks, in the earlier videos of these talks. But here now we see the organization of the model in the graphic user interface, and here we can see for the three syllable oscillators, we are just modeling here a nonsense word bus cum tip, 3 syllables. This is the oscillator for the first syllable, for the third syllable, for the second syllable, and we can see the neural activity occurring in this two-dimensional oscillator, and the activity is given here. We can see that now in a video. Yeah, first of all, why oscillators? The point is oscillators, that is the same in the articulatory phonology. Oscillators define time intervals, and thus they define duration of time intervals. So the time interval defined by an oscillator is the duration, perhaps the duration of one oscillation cycle. So oscillators define that what we call that we have a sense for time as a biological system. So, and here the oscillators define the timing of actions. Action may start at specific points, or at least they start at specific points in time within an oscillation cycle, and they end at a specific point in time, and these specific points in time are phase values in the concept of oscillators. So the oscillators is defined by a frequency, which defines the duration of an oscillation cycle, and phase values, which define the points in time within one oscillation cycle. So the timing of articulation, yes, and why are we using this concept? We are using this concept because we know from experimental results that the timing of articulation remains more or less phase stable concerning the phase values, even for different frequencies of oscillation. That means for different speaking rate. Why is the frequency of oscillation of the syllable oscillator defining speaking rate? Because an increase perhaps in frequency reduces the duration interval for a cycle, and that for a whole syllable, and that changes the speaking rate, or at least the duration of the syllable production, and thus the speaking rate. So here we have nearly the same plot of the graphic user interface, which can be produced by NENGO, and we will now see a video where we can see the activation of the 3 syllable oscillators and the initiation for the start for each syllable. So I will go to the video and now start the video. So if we start with these NENGO graphical user interface, we need a longer time here, about a minute, I think, for the preparation of the simulation. Yeah, and then there is a point in time where the simulation starts, and I will start here. So and now we see, So now I see the pulse for the first syllable oscillator starts, and here we have the oscillation for the first syllable, defining phase values where gesture should be activated. So now this was activated. Now the second syllable the syllable oscillator, the second buffer becomes activated with this buffer. And we will see now the third syllable will be activated here. And what we see I will stop it and go back again. What we always see is, or I should already inform you concerning this, it is at least this part for each syllable. So we see here the oscillation for each syllable, and in this quarter of the oscillation of the counterclockwise oscillation cycle, the syllable is really produced. So the phase values for starting the first consonants are about here. The phase values for the end of the last consonant action, is about here. So that's why the activation of the second syllable in time overlaps with the activation of the first syllable. I can show that again. So we will see in the next video here the first consonant starts. Here we have the mean activity of the vowel. Now the last consonant starts, and here the syllable activation stops and the activation for the first consonant of the next syllable starts. Here the articulation of the second syllable stops, and now the articulation of the last syllable, the first consonant of the last syllable starts. So it could overlap in time a little bit more for fluent speech. Okay. So, oops, going back. Okay. Going further to the next slide. So now we saw how the syllables bus, cum, and tip can be activated one after the other by initial pulses and a little bit with overlap in time. And now I would like to introduce you how each syllable oscillator is able to activate gesture oscillators. So here for the syllable bus, we will activate the oscillator for the syllable A, for the gesture A. Here is the activity of this gesture. But first of all, before we activate the gesture A, we have to activate the gesture for B, which is a labial closing gesture. That is, that is this oscillator. And last but not least, for the oscillator for the S, that is this oscillator. The activation of these three oscillators is given here. So, and what we see here for the gesture oscillator, the degree of neural activation, of course, and it is similar to the degree of realization of each gesture. What we see here. Here it is just a generation of time values. For the syllable oscillators, it is just a generation of time values as phase values in a two-dimensional space. Here we have a one-dimensional space, which is degree of realization of a gesture. Here between 0 and 1, and this is the time axis. Here we have no time axis, the time is just a parameter. Okay, I will come to this a little bit later. First of all, let's have a look on the video the video will now show how at specific phase values here in this oscillation cycle, that at specific space values the gesture activation starts. So, yes, one more explanation. If you see the videos, you can start the videos from the PDF file by clicking here, but now in this presentation I have embedded the videos in the presentation. So, let's have a look at the video. It just presents the oscillation cycle for the first syllable. We again have to wait a time until things start. Concerning the initiation process, so here the preparation of the model is done and the simulation starts. So I will start it. Oops. So here we see, and I told you at this point in time, here the first consonant activation starts, first gesture, and the vowel gesture as well. And now the last syllable, about here, the activation of the last syllable starts. And here all is done. Okay. Coming back to this point in time. Sorry, I have to stop it here. Let's have a look again. Yeah, so we see at this point in time here, we have the onset for the first consonant gesture B, and at more or less the same time in the background the vocalic gesture is activated, but very fast the maximum is reached. That means the degree of realization of the consonantal closing gestures for the B is already reached, while the vowel is still not at its target level. So at least here the consonant, the initial syllable initial consonant is finalized, but so now we concentrate on the vowel action. So, and we see at this point in time here, at this phase value, the syllable final gesture starts, the S syllable. So, and here more or less all is done. We have reached the target for the syllable final consonant. So we see that these phase values defined by the syllable oscillators define the starting and the ending of the gesture oscillators. Why do we define the gestures by oscillators themselves? Because at least we have a time, an intrinsic time scale here as well. You can see that the consonant gestures are faster. That means that the target, that from the point in time when the gestures start and when the target, that means the closure, is reached, this time interval is very small. It's not that small for the vowel. So that means we need a higher frequency for consonantal gesture than for vocalic gesture. So the frequency of these gestures defines the time interval for realizing a gesture, for bringing a gesture from its initiation to the target, so where the articulation target is reached. Yeah, let's have a look on all of this in this next video. That this may give a better explanation how this degree of realizations of gesture plots can be interpreted. At least they can be interpreted as abstract movement trajectories. We will see that if we see the articulation as it is done by using our 2D articulatory model. What are these lines meaning? They mean that in our plots for the neural activation levels for each gesture, the target in the abstract movement trajectory, if we interpret these neural activations as an abstract movement trajectory, that the target of a gesture, that means the full closure for a consonantal gesture or the near closure for a consonantal gesture or the vocalic target, is reached earlier than here. It's already reached at about here. But this trajectory here, or at least this change in degree of neural activation, represents the velocity of an articulator. That means how fast the articulator reaches a target. That means a full closure or the vocalic configuration. So for that, let's have a look at the video. First of all, we will see the articulation for the syllable bus here using our 2D articulatory model. So now starting now, B, A, S, or now a little bit slower. Start. So B, A, S. And I think we will see it further time in slow motion. B, A, S. So I will stop the video here and go back. So So here the starting point for the syllable, and this movement trajectory here, which is, at least in our model, coded as a change in degree of neural activation. At least it's not a real movement trajectory, it's a kind of abstract movement trajectory. This gives us an impression about the articulatory velocity and about the degree of realization of a gesture. That means how far are we away from reaching the target. That means here the full closure, here the near closure, or here the vocalic position. So, going to the video. So this is exact the time interval where this is done. So we reach the closure, we are now at this point, and what we see is that behind this closure, we are already preparing the vowel. So what we see during this closing interval is that the movement concerning the lowering of the tongue position towards the R target is going on. So we see that is going on. And now we have the opening. So here we are in the middle of the R. And now the consonantal transition for the S starts. And now we are at this point in time here, the target point. Okay. Okay, so what is the first application, the first perhaps scientific application of our approach, or why do we think that this approach using oscillators is realistic? One point is that modeling different speaking rates is very important. Speakers are free in choosing different speaking rates up to the conversation situation. So, and the point is that phase values are more or less constant. They are describing the timing of the speech actions at syllable level. And we did not mention that before, the oscillator frequency of the gestures, of the actions, of the vocalic and consonantal actions stays consonant as well. We have seen this oscillator frequency is fast for consonantal, a little bit slower for vocalic gestures. So it defines different types of sounds and should not be varying so strong. So this stays constant. But we can vary the oscillator frequency of syllable oscillators, and that, as we discussed earlier, may implement different speaking rates. So last but not least, we did a first simulation for increasing speaking rate just by varying the oscillator frequency on the motor plan level, not on the gesture level, and we did not vary any target values. So the timing of the gestures within a syllable concerning the target, concerning the phase value stays constant, and we get from slow over normal to fast. So what we see is that here, for our three gestures, bass, cum, dip, the articulation here of the consonantal gestures, and here we see the vocalic gestures, and here we see some other gestures like the velopharyngeal gestures and the glottal gestures as well. So what we see is that these gestures overlap in time more and more and reduce in time, but what we will see as well is that the articulatory velocity for each of the gestures more or less stays constant. But nevertheless, because the overlap in time of gestures increases and the duration of each gesture decreases, we get an increase in speaking rate. Here normal, here fast. So back again from slow to normal to fast. Okay, so now what is the work we have to do? You have already seen we have a 2D articulatory model. We have already a concept how to realize the motor plan level and the gesture level for controlling speech articulators, but what we have not done so far is a real-time integration of the articulatory-acoustic model into our neural brain model. This integration would allow us to generate acoustic and somatosensory feedback signal on the fly, which is important for modeling motor learning. For example, the timing of, or the points in time for the begin and release of constrictions are not directly given by the phase value, and by this they are defined at least during the articulation and generation of the acoustic output. So that means we can get information, somatosensory information, and of course acoustic information, and this may allow us to learn the motor relations. So the implementation of an articulatory model is not thus difficult. We have available 2D articulatory models, as we have seen in the video before, and I would like to invite you to download the speech articulation trainer from the App Store or Google Play, which already shows you an implementation of our 2D articulatory model. For example, it's good for teaching. So yeah, and last but not least, so we have already implemented this and can control this model, but we have not integrated it in the whole simulation cycle. So we cannot control on the fly auditory, that means acoustic output, and speech movements, which represent somatosensory output at least, which is important in order to have this control loop complete, and thus to enable us to learn the set of motor plans, or the most important syllable structures for a language. Yeah, that's all I wanted to tell you. Thank you very much for your attention.